Next, we will talk about the Bernoulli distribution and the binomial distribution. I normally like to talk about a Bernoulli random variable, and then we will talk about the binomial random variable in a bit. Okay, remember we are dealing with discrete distributions. So first, let's talk about the Bernoulli distribution. Yeah, Bernoulli distribution. Okay, let's read some of the things they have written here first, right? A Bernoulli random variable x, right? A Bernoulli random variable x can only take the values 0 and 1. So let me draw a little table here. X equals to x and probability x equals to x. Okay. So what are the values that the random variable can take? 0 and 1. The probability that x equals to 1, let's give it p. And because there are only two values it can take, okay, the only two values this x can take. So if I say the probability x equals to 1 is p, so the probability x equal to 0 must be 1 minus p, right? So this 1 minus p, sometimes we like to call it, okay, this 1 minus p, sometimes we like to call it q, okay? So that's what I've written here. A Bernoulli random variable can take values 0 and 1, and 0 we can classify it as failure, and 1 can be a success depending on the person doing the experiment. Yeah. So 0 can be classified as a failure and 1 can be a success. And I've just mentioned this idea here. Okay. I've just mentioned this idea here. Um, very quickly, right? What is in statistics, right? We come across something called a Bernoulli trial, right? Okay. Uh, I'm trying to tell you what a Bernoulli trial is. A Bernoulli trial will only have two outcomes. Okay, Bernoulli trial will have only two outcomes. So when you toss a coin, right? When you toss a coin, how many times? Once. Okay, when you toss a coin once, we call it a Bernoulli trial. There are only two outcomes, heads or tail. And so if you call, getting heads a success, then the probability of, of h will be equal. Let's say we give the value, right? The probability of h equals to 0.7. So we'll say p equals to 0.7 again, right? Uh, we have tossing a coin, right? This coin, you toss it once, and that's called a Bernoulli trial. And that's because it only has two outcomes. So if you call getting a hits a success, so the probability, and let's say you give that a certain value, right? Let's say probability of getting a hits is 0.7, so p will be 0.7. And so probability of getting a tails must be 0.3, and we'll call q equals to 0.3. But what do I want you to take away first? I want you to take away the idea that a Bernoulli random variable will be like this, okay? The Bernoulli distribution, yeah? Let me just quickly write it again. Take me a minute, okay? A Bernoulli random variable for you. When we talk about a Bernoulli distribution, let me tell you again. When we talk about a Bernoulli distribution, I repeat, when we talk about a Bernoulli distribution, it can take values 0 and 1, okay? And the probability of getting a 1 will be p, and this will be 1 minus p or q if you like, okay? Good. So what's the expected value? This, let me write it here, right? So that there's no confusion, right? This is your Bernoulli distribution, okay? Quite easy. So the expected value of x will be 0 times something is 0, 1 times p is p. There you go. And if you can also work out the variance, okay? You can work out the variance, which is actually quite easy to do because the expected value of x squared, right? The expected value of x squared will be what? Let me get that right. Expected value of x squared will be this one, no big deal, right? 0 squared is 0. So this will be 1 times, it will be p, okay? Okay, so we have variance of x will be this one. Expected value of x squared minus the expected value of x squared, right? Remember, second moments minus first moment squared. We have this. So you take this out, you'll get 1 minus p. There you go. Okay. So for Bernoulli distribution, They can take two values. Again, for Bernoulli distribution, they can take two values, 0 and 1. The expected value of x will be p, and the variance of x will be uh, p times 1 minus p. Good. Enough about the Bernoulli distribution. I want to talk about the binomial distribution. Okay. So this binomial distribution is very important for you. Okay. We use binomial distribution quite a bit, even in finance theory. So let's learn it. Yeah. Remember, in the Bernoulli distribution, we only had one trial. Okay. The Bernoulli distribution, we only had one trial. You either have a 0 or a 1, right? Or you either have a head or a tail. That's it, right? Are you with me on this? So let me tell you again slowly, right? When you talk about the Bernoulli distribution, you only have one trial. You either have a 0 or you have a 1. That means it's a two outcome situation, one trial. That's a Bernoulli distribution. The expected value of x is what? P. And the variance of x is what? P times 1 minus P. Okay, enough about that. But in the Bernoulli, in the binomial distribution, okay, in the binomial distribution, we have got what? N Bernoulli trials, right? Okay, N Bernoulli trials. And I better write this thing here. Okay, so the binomial distribution, we have N Bernoulli trials, but they're independent trials, right? Okay, here we have got N independent trials. So which means if you, let's say, for example, you toss a coin 5 times, okay? You toss a coin 5 times, you have got 5 Bernoulli trials. They're all independent, okay? Because what happens on one toss does not affect what happened before and what happens after, right? So we've got N independent trials, and the probability of success, we like to call it P, okay? So the probability of success is P. Be careful about all this notation, right? The probability of success is P. Now, if you say X is a binomial random variable, careful. If you say X is a binomial random variable, what does it represent? Listen very carefully, right? I've already told you two things. One, we've got N independent trials. Two, we are defining the probability of success as P, okay? And now we are saying, if you call X the binomial random variable, if you call X the binomial random variable, what does it represent? It represents the number of successes in N such trials. Okay, so I have N trials, I have P is the probability of success, and X, the binomial random variable, X, the binomial random variable, represents the number of successes in N trials. Okay, now this is the formula. Okay, let me write it here. Okay, hang on. Let me just clear this, right? And I'll write it here again. Probability, if you have a binomial distribution, right? The formula for a binomial distribution will be probability x equals to R will be what? NCR, PR, Q, N minus R. Okay, that's what you see here. Okay, remember what X is, right? X is a binomial random variable, and it represents the number of successes in N trials. So if I tell you X equals to R, means it's R successes, right? Okay, so it's NCR P to the power R, Q to the power N minus R. And what are the values that R can take here? Okay, R here stands for number of successes, yeah, in N trials. Okay, so please be careful. R can take values from what? R can go from 0 all the way up to N. There you go. Okay, you can have 0 successes. I repeat, when you throw a coin 5 times, And if you call a head a success, then you can get all tails, right? Which means you don't have a success at all. So that's what I mean by R can be 0 and go all the way up to N. You can have all your 5 tosses coming out as heads, right? That's the story. Good. So we want to talk about some definitions quickly. The parameters for the binomial distribution, right? The parameters for the binomial distribution are N and P. Okay. N and P make up the parameters of a binomial distribution. It means that if you are given N and P, the binomial distribution is completely defined. Okay. Okay. Next, the expected value of X will be, so if you have a binomial distribution, the expected value of X, okay, let's write it here, will be NP. And the variance of X will be NP 1 minus P. Okay. So there are various derivations for this, there are proofs and all that. So make sure you know this. The expected value of X will be NP and the variance for X will be NPQ. You can remember this from our Bernoulli distribution. Our Bernoulli distribution, we said what? The expected value of X is P, right? Right? But now how many independent trials do we have for the binomial distribution? We have N. So it's just N times P. Same thing for the variance of X. Here we have P times 1 minus P. That's for the Bernoulli distribution. But now for the binomial distribution, we have N such trials, and they're all, they're independent. So it'll be N times P times 1 minus P. Not difficult, right? I've written all those things here, and that's about it. Okay, good. So now let's look at an example, right? Let's look at an example. Great. Read the question carefully, right? During one policy year, right? One policy year, a certain life insurance policy either results in no claims with a probability of 0.99. Okay. So no claims is 0.99, right? Let me write it here. Probability of no claims. So no claims. So probability of, let me just write here, 0 is 0. Okay, good. So no claims. When the policyholder is still alive, or results in a single claim if the policyholder dies. So probability of a claim would be what? 1 minus 0.99, 0.01. Okay, so good. So we have, if you like, you can write this as probability of 1. Okay, this is why I wrote probability of 0 is 0.99, probability of 1 is 0.01. So now let's see what they want. X represents the number of claims during one policy year. So what does that mean? Remember, X can either be 0 or 1. Find the expected value of X, sigma X, and the moment generating function. Okay, so I will write it here for you. I'll come back to that in a minute. The moment generating function of X will be what? The expected value of e to the power of tx. Okay. Okay, let's look at my solution. Because it can only take 0 and 1, okay, it can only take two values, 0 and 1. So X is a Bernoulli random variable. Probability X equals to 1, I just gave it to you, is 0.01. And let's just call that P. So we know from our early discussion, the expected value of X is just P. Expected value of X is just P, so it's 0.01. And the variance of X is what? P times 1 minus P. There you go. Okay, P times 1 minus P. What is 1 minus P? 0.99, correct? Excuse me. What is 1 minus P? 0.99. So I have 0.01 times 0.99. You'll get your answer. That's the variance though. But here they threw in a spanner here. It's not variance. They want the standard deviation. Take the square root and we are done. Okay. So we're just using two formulas, Pn, P times 1 minus P. Good. Great. Now we're looking at, they want what? They want the moment generating function. That's by definition, the expectation of e to the power of tx. And what's the good news? Remember, expectation, there's a summation, right? So what are the values x can take? 0. So it will be e to the power of 0, right? Times, what is the probability x equal to 0? 0.99 plus, what's the other value x can take? 1. So it will be e to the power of t. And what is the probability x equals to 1? 0.01. That's the answer, really. Okay, here you go. Can you see? This one here, e to the power of t times p plus e to the power of 0 is 1 minus p, and you'll get your final answer here, and we are done. Remember, e to the power of 0 is what? 1. So you have your final answer. Not hard to do. Okay, let me clear the screen. Good for us to know the following, a couple of formulas that follow now. I'll just tell you very quickly. Okay. Here, we are looking at the moment generating function. No, I've done that already. For x, right? Remember, I told you that if you have a binomial distribution, it is completely defined if I give you the value of n and I give you the value of p. Okay? So if I give you n and I give you p, it's completely defined. So we like to write x is binomial with parameters n and p like this, right? So the moment generating function is quite good for us to know q plus p e to the power of t all raised to the power of n. That's the MGF, right? The moment generating function is q plus p e to the power of t. Okay, q plus p e to the power of t all raised to n. And the PGF, okay, the probability generating function is just q plus pt all raised to n. Now, you can actually see this. Let me clear this, right? You can see this formula without doing too much of thinking by looking at this thing here. Can you see? Okay, no, let me just clear that. That's not okay. I want to say this, right? This thing here, okay, we are dealing with a Bernoulli distribution, right? We are dealing with a Bernoulli distribution here. So which means your number of trials is how many? Just one, right? So it'll be Q plus P T. This is N, right? N is equals to 1, right? So let's not write 1, okay? It's given it's 1. So you get the answer straight away if you know this, right? Q you know is 0.99, P you know is 0.01, and we have got the answer straight away. Okay, for your, okay, are you with me on this? I'll repeat, right? This one here is for the binomial distribution with n trials. But if n equals to 1, then your probability generating function will just be q plus pt. So you just write 0.99 plus 0.01t. Okay, if the question had been probability generating function, but our question was what? Moment generating function, right? So the moment generating function is given by this. This is for the binomial distribution, right? So just make your n equals to 1. You'll get it for the Bernoulli distribution. So it'll be 0.99 plus 0.01 times e to the power of t. There you go. It's quite easy to do. Yeah. Okay. So it's very useful for you to know these formulas. The moment generating function, q plus PET. I call it PET. I actually memorized some of these things. Q plus PET raised to the power of n, and then I have q plus PT raised to the power of n. Okay, one is for the moment generating function, one is for the probability generating function. Okay. Okay, so I tried to tell you these using numbers here, and I've written it in words here. Let me just read this. the MGF of a sum of independent random variables. This one I said it in one of my videos previously, right? The MGF of a sum of independent random variables. I think I used x plus y. Okay. Okay. Is equals to the product of the individual moment generating functions. Okay. The moment generating function of a sum of independent random variables will be equals to the product of the individual MGFs. So that's the idea here. Okay. For your binomial distribution, we have a sum of independent Bernoulli trials. Okay. So you can write it like this, and then you can write it like this. Remember, it's a product, and you have your answer coming out here quite nicely. Okay. Excuse me. So let me give you a summary. What is the important takeaway? If you have a binomial distribution, you have n trials, and the expected value of x is np, and the variance of x is npq. And the moment generating function for a binomial distribution, the moment generating function for a binomial distribution will be q plus p e to the power of t all raised to n. Okay. And the probability generating function for a binomial distribution will be q plus bt all raised to n. So these are very powerful formulas. We will have opportunities to use them, and we should be able to get through them quite easily.